Greetings, and how you guys doing? Imagine you are working on an AI project, processing data step by step and cleaning it, transforming it, and feeding it into a model. But suddenly, the code gets messy, repetitive, and hard to manage. Sound familiar, right? What if I told you there's a better way to structure this process? Introducing the pipeline design pattern. Firstly, let's talk about what is a pipeline. Pipeline is a sequence of data processing steps where the output of one step becomes the input for the next. It's like an assembly line in a factory. Raw machines go in and the finished products come out after passing through the multiple stages. Imagine you are running a juice shop where you process fruits. It's like an your data into a final juice products. Final juice products like the trained machine learning model. The pipeline is like the steps in your juice machine. Each step has a specific task, and the out of the one step goes to the next. And what the pipeline does, think pipeline as a conveyor belt with three steps. Step one, cleaning the foods. It's like in ml scale. Get all the foods into a standard size. Step two, peel and chop them in ml terms. It's like a PCA, erased unnecessary parts and focus only the juiceable parts. Step 3, juice them. In ML, it's like a classifier. Create the final juice products, a model that makes predictions. So let's simplify this pipeline steps. Here is what happens in our code pipeline in plain terms. Step 1, scaling the data. When we input raw numbers, they might have very different scales. For example, as a feature one, let's think we are enter like measurements of the flowers. For an example, feature 1 as petal length, values range from 1 to 10. Feature 2, let's get saber length, values range from 1 to 100. Okay, some ML algorithms like PCA. PCA means principal component analysis, sensitive to these differences. So we scale all features to have same range. You can see it in this slide to ensure no further dominates others. As an step 2, we can get dimensional reduction. In this, we use we are earlier discussed about PCA method, principal component analysis. Imagine we have a photo of flower with lots of details, examples, and petal and samples. You want to summarize most important features of the flower without keeping every pixel of the photo. That's we are called dimensional reduction. So as an step 3, we can define classifying the data. We can use here right random forest classifier. This is where we actually learning from data. After scaling and PCA, the data flows into the random forest classifier. The classifier builds multiple decision trees. So you can think of them as if then rules to predict which flower specifies species each sample belongs to. You know, there are different kinds of flower species. It's like Setosa, Virginica, etc. So why these pipelines are useful? Let's talk about. Without a pipeline, you do need to do manually. Scale the training data, apply PC on the scale data, and train the classifier. As well as after that, you need to repeat the same steps on testing data. A pipeline ensures this workflow is automatic and consistent. So before we go into move further, let's recap our food machine learning model. Okay. So I mentioned earlier, clean the food is a scaler, peel and chop is a PCA, choose is a classifier. As a description, scalar is make sure all foods are same size. PCA means focus on the juicy parts. Scalar means create a final juice. So now you can understand the pipeline design pattern is all about creating a reusable workflow that can be applied to different tasks. So how the pipeline patterns works in general? Actually, pipeline pattern is like a template like this. Firstly, find the step that process data sequentially. Connect these steps into a pipeline. Apply the pipeline to any dataset or program where similar pre-processing and modeling are needed. So let's get an example as image processing. If we look into the image processing pipeline steps, we can say, firstly, we need to resize images, make all images same size. For an example, 128 pixels. And secondly, we need to normalize pixel values, scale pixel values into range between 0 and 1. As in step 3, we can feature extraction. Use PCAO, another method to reduce the number of features. As an fourth step, we can train the convolutional neural network. In simple terms, custom CNN model or random forest to classify images. So let's get into as an example too, we can get text classification. Now, now suppose you are dealing with the text data and examples, emails and tweeters. So as pipeline steps for text data, we can say, firstly, we need to clean this text, like remove punctuations and convert to lowercase. Secondly, convert text to numerical format using techniques like TF-IDE. Thus we call a vectorization. And thirdly, use a model like logistic regression to classify the text. That's we call as a classifier. So, and let's get into another code example here. So, what are the key benefits of this pipeline pattern? Firstly, we can say reusability. That means you can apply the same pipeline to different datasets or problems with similar processing requirements. And secondly, modularity. Each step, each step in the pipeline can be swapped or modified without affecting the entire workflow. Actually, as an example, we can change PCA to another dimensional reduction technique like TSM, as well as replace random forest classifier with a radiant boosting machine. As well as third benefit of this, we can say ease of deployment. Once built, the pipeline can be saved and reused later in production for new data. In fourth benefit, consistency, ensuring that some pre-processing steps are applied to training, verification, and testing datasets. Ah, another matter. Can we exact pipeline be used for flowers, images, and text? What do you think? As a short answer, yes, the pipeline structure remains the same. But no, why? The specific steps, I mean components, in the pipeline will change depending on the type of data. Data types like numerical, image, or text. So why structure stays same? Actually, the pipeline design pattern is like a universal machine. Input data goes in, it gets processed in steps, the final output comes out like predictions. So we need to always pre-process the data, transform it to an useful form, train the model and make predictions. So this general structure works for any kind of data, numerical, images, text, audio, etc. That's why I say structure is the same. So why the component need to change? Each type of data has unique characteristics. Specific tools and transformations must match the data type. But how? For an example, let's get flower data. Flower data are numerical, right? So input flower measurements. Example, petal length, stable width. So what is the pipeline component here? As an scale, we need to normalize numerical values. So as as a PCA, we need to reduce dimensionality to focus important features. Okay. And what about random forest classifier? We need to classify flowers based in measurements. Okay. So what about the image data? According to the image data, we can get as an input a raw pixel values of images. Example 1 to 8, 1 to 8. So what about the pipeline components? We can say resize, ensure all images same dimensions. And so what about feature extraction? PCUCNA extract the most meaningful patterns in images. As an classifier, finally, we need to classify these images. As an text data, for an input, we need to add protex pipeline components as text cleaner, vectorizer, and finite classifier learns pattern in text to make predictions. Now you can understand, right? Why the components need to be changed. So can we process different but same type of data in same pipeline? In short answer, yes. But how? Let's see. In a code example. So the beauty of the pipeline design pattern is flexibility. Reuse the same pipeline structure, but adjust component for specific task for dataset. So guys, that's it for today. Let's meet another interesting video in next week. So until then, take care and peace. Bye bye.